number in the list?
No, so that's alluding.
It's alluding to the fact that we're looking at upper bounds. Yeah, absolutely. And we're going to get more into that here in a second. Okay. So let's get into the counting, okay? This is giving us an idea of what we're doing here. You know, this is giving us kind of a ballpark as to how many statements we're going to be executing, right? But as other people have already pointed out, we are missing a few things, right? So for instance, we're going to ignore the signature, okay? At the top there. There's stuff that is going on here when we say int, total, and all that other stuff when we call something. But we're assuming that it's constant, it's going to be the same for all our methods. And we're just going to ignore that, okay? We're worried about what is actually going on, the content of the actual method itself inside of the method. All right? So the first thing we need to worry about is this right here. So this int result is equal to 0 is going to take how many statements? What is that? It's a 1, right? This is a 1, okay? What about the return?
1.
Okay, return is also going to be a 1, okay? Now we have to talk about the for loop. Now, what's nice about a language like Java is they take essentially 3 different statements and they combine them all into that one for clause, right? We're going to have to decompress them. And we're going to talk about each of those little parts by themselves. But let me just go ahead and write them out first so we can look at it. I'm going to go ahead and change values.length to n. And then I'm going to put it, then we get the I++. So this is what we're actually doing here, okay? So let's look at this. We got the int I equals 0. How many times do we execute that? Once, right? At the very beginning of our for loop, we have to initialize our variable to 0. We do that only one time, right? I'm sorry, it's hard to read that. Let's look at this. How many times are we going to update I?
Every time we go through. N times.
N times, right? Okay, so initially it's 0, right? Let's say that n is 3, or 4 in this case, okay? So we're going to start off at 0, we're going to add 1, we're going to add 2, we're going to add 3, we're going to add 4, but when we get to 4, it's going to be the same thing as n, so we won't update it after that, right? So how many times do we do it? We did it 1, 2, 3, 4, right? Because this is the initialization, and then every time through the loop, we're going to add 1, 1, 1, 1. And the last time through the loop, we're going to add 1, but we're not actually going to execute the loop, but that doesn't matter. This is going to be n, okay? So our I++ is going to be executed n times. How about this one right here? Did you have a question, Jim?
Well, I was going to try and answer it, but
Okay. No, that's fine. Go ahead.
well, it's got to check that each time that it goes through. So I'm thinking that first it is calling n, and then it's doing a comparison between n and a value. So I'm thinking 2 for each, or is that just one statement for each?
It's only considered one statement.
One statement for each time it goes through the loop, so n times.
Is it n times?
I don't know.
I think you're right. Okay. We set it to 0, right? We have to check it that first time through the loop, don't we?
Yeah.
Right? So when you can't start the for loop until you check it, right? Then we have to check it each time we increment I, right? And we're going to increment I until it gets to 4. Now we're going to check it this last time, and it's going to be false, but we still have to check it, right? So this is going to actually be what? N plus 1 times. Okay? So everybody follow that?
So did you?
There's the initial check, and then we have to check each time we increment I. And since we increment I, well, in this case, 4 times, but n times, we're going to do it one more time because we had the 0 in there as well. Does that make sense, Clay?
So you gave, you gave 4.
It was just an example.
Yeah.
I was just saying that.
You're
let's say
saying
that
n
is
equals
equal to
4.
Let's say that n is equal to 4.
Okay.
And what would it look like? I just wanted to give you an example.
You're good.
It's harder to look at in the abstract, as far as that goes. All right, so then what we do is what? Then we go ahead and we total all this up. So we said that this is 1, right? So we have 1, 1, 1, and then 1. So that's 3, right? Or that's 4, right? And then we have n how many times? We got 1, 2. Wait, what's 1, 2? Is that just, what did I do? Oh, yeah, one more thing. Yeah, oh, I'm sorry, we're not done. We're not done. Sorry, my bad. There's one more thing we have to consider. Now, we have the return result, but what else do we have to do here?
Actually added.
You got the result. We have to update the result, right? Plus equal, right? How many times do we do that?
N times.
N. Because that is the number of times we execute the loop. We're going to get to that particular clause or that one particular statement N times. Okay? And then we add all this up, and then what we get is 1 plus 1 plus 1 plus 1, and then N, so we're going to get 3N plus 4. And the way we usually specify the number of statements or the amount of time in terms of N is we usually use T of N. It's just a convention we use. T of N is the number of statements that we execute for this particular part of function. So in this case, it's 3N plus 4. So if we have a array of size 10, it'd be 34. Okay, would be the number of statements. Okay, does everybody follow that? This slide right here just summarizes what I just said. So if you need to go back and look at it, you can. And T of N is the number of executable statements in the method. In this case, total. Okay. Now, when we're trying to do this, the easiest way to try and compare things, so let's say that we have let's say that this is the T of N for this particular, program that we just ran. Let's say we have another one that runs at that time. Which is faster? It depends on what N is, right? But the growth rate, in other words, the slope of the line, is it really going to be that different? No, it's not, because they're linear, right? It's a linear function. If we're comparing this to like an x squared or 2 to the n or something like that, we can say that they're in the general same family of each other, right? And the reason is because they all are linear in n. The overall growth rate is not going to be that much different. It'll be within a constant of each other. Okay? So, like say for instance, okay, so your grade through this course, right? It's not going to, when you look at your transcript, it's not going to say project 1 you got 100%, and project 2 you got 75%, and then project 3 you got 90 or whatever. What is it going to do? It's going to give you a letter grade, right? Maybe it's like a B or a B plus or whatever it is. It's the same idea when we're talking about these growth rates, and we're trying to compare the number of statements executed. We're going to look at the class or the categorization of these number of statements as opposed to the actual details. So we're going to we're going to simplify some things so that we can get to the heart of what's going on here. Okay? And that's basically what we're talking about. So we're looking for the dominant term. Because again, what we're talking about is when n is getting really, really big. And in fact, you can even say as it approaches infinity. If we've got a really large n, say 1 billion, is this 4 really going to matter?
No.
Or the 6? The terms that you're going to be worried about are these two, right? Okay? And so that's part of the simplification. Let me just go on to the next slide so we can talk about that a little bit more. How we're going to characterize these things. And what we use is what is known as big O notation. And big O is just a big O. That's all it is. Okay? There's also a big theta you might hear of. For those of you who are comp sci majors, you will get more of this down the road. And then there's also a big omega. What we're talking about is big O, and we're talking about an upper bound. Okay? What we want to know is, we want to know how big this is how bad it's going to get, but no worse. In other words, we don't, we could say that it's, there's some sort of, like n factorial is the worst growth rate we can come up with. But we want something that's tighter than that, right? We can say that everything is upperly bound by n factorial, but we want to get something that's a little bit closer to what its actual value is, right? We want as tight of upper bound as we can get. So it's meaningful, right? if everything has an upper bound at n factorial, it's not meaningful. You know, it doesn't really make any difference. All right, so what we're talking about is big O is the asymptotic execution time of the algorithm. As n gets really, really big, how bad is it going to get? All right, it's an upper bound, it's mathematical. And what we want to do is we want to get out of the unimportant details. We want to figure out where is the real substance of this. What are we really worried about? And what we talk about is we talk about a function that we can describe in as simple a terms as possible that's going to give us a characterization of this particular method. Now, this is a definition. You don't need to memorize this. I'm just going to throw this up here just to let you know that what we're talking about is we're talking about your T of n is bounded from above by some function. Okay? That's all you need to worry about. You think about it like this. And let's say we had this function right here, and we had this function right here, okay? So let's say that this is g of n, and we say that f of n. So which one's the upper bound? Can we say
Depends on where.
It depends on what?
Where you are.
It depends on where you are in the graph, okay? So what we say, I have to get some more markers. I'm running out. So what we say is this, is that as long as after some point, we usually call this n naught, as long as g of n is going to be an upper bound or greater than g of n, or f of n, for all the rest of n, then we say that f of n is in the big O of g of n, okay? We don't have to say it has to be true of all n. It just has to be, as long as it's after some point, and everything beyond that is true, then what we have is we have this situation where it's an upper bound. That g of n is going to be greater than that, okay? All right. And then they talk about these constants. Again, I don't want you to get into those kind of details. I just want you to get kind of a feel for what we're talking about there.
How do you read the f of n is, how do you read that little thing again?
F of n is in the big O of g of n.
Okay.
Technically, and I don't want to get, I probably shouldn't introduce this, but I'm going to. Big O of g of n is actually a set of functions. And what that is it's going to be a set of functions that have a growth rate that's equivalent to g of n or less. Okay? It's an upper bound. It's all of these functions that you can include under the graph of g of n. Okay?
I just wanted to make sure it's the same.
Yeah. Yeah.
So what this is saying is, worst case scenario, this is how my program performs. Is
Exactly.
that basically what you're asking?
Right. But we also, again, it's not just the, we just don't want to say that, but it's also as tight as possible. We want to find out the function that is close to our program without going over it, right? Right?
Yeah, so that graph accurately displays what it would work like.
Exactly.
in the worst
Yeah,
case
exactly.
scenario. Okay.
Exactly.
So the units on the y-axis is f of n equals.
Yeah, well, yeah, it's going to be some function of n. Yeah, absolutely. So it'll be, well, it'll be either g of n or f of n. Depends upon the situation. It's just some function of n. Okay. Again, t of n is our actual growth. F of n is a function that's going to bound that growth rate. Okay. So actually, if I wanted it, what I should have done is this, just because of the terminology we're using. This would be t of n. This would be f of n. And then we'd say that our t of n is in the big O of f of n. Okay. It's the same idea, but this is specifically with the terminology we're using. It bounds the rate of growth of our function. It may be, and there's, okay, so there may be an upper bound. That's what we're talking about is big O. Lower bound is actually our big omega. Okay, but don't worry about that stuff, okay? And it may not necessarily be equal to it. Constants and lesser terms are ignored because it's a bounding function, right? It's putting it in a pen, so to speak. It's only allowing it to go this far. So what we're going to do is we're going to ignore constants and lesser terms. So for instance, if we're talking about our, let's say that we had T of n is equal to 2n plus 6. What is big O of this going to be? We're going to ignore the lesser terms, right, which is 6. We're going to ignore the constants, in this case is 2. So what is big O going to be?
N.
N. Okay? Right? We're trying to get down to the pith of it. We're trying to get down to the heart, the essence.
So mathematically, would you just look at these in terms of like your parent function?
Yeah, absolutely. Yep, that's one way of looking at it, absolutely. This is just a little bit more detailed. Yeah, Jimmy.
Yeah. Could you go back?
Where do you
What
want-
it means one,
What's that?
the what it means, or, you know, go forward on what it means.
This,
There we
okay.
go. The last bullet there. So which is the bounding function, f of n or t of n?
F of X.
F of n. Okay.
Yep, it's the bound, right? That's why we have it in the, it's the big O. It's a set of functions. So it includes T, it also includes other things as well. Okay, this is the definition, and what I want to show you is basically this, so we can kind of see that, you know, time for the algorithm to complete, simplified number of executable statements, okay? And so essentially what we're saying is that this is our f of n, and this is c times our f of n, and essentially what it is that we just want to show that this is a bound, okay? Don't get too caught up in the details of this. It's just kind of show you the general terms what's going on here. All right, so what does this mean? So this is, again, this is just a reiteration of what we were just talking about. So for instance, f of n is a sum of several terms, and we keep the one with the largest growth rate, omit the others, and then what we end up with is this. So, yeah, I've got to correct these slides because this is, it's being inconsistent. I apologize for that. Let me just show you real quick what we got up here. So our T of n in this case is n squared
We're just taking the largest.
plus n plus
bound
1.
of n.
Okay? What is our big O going to be then? This part,
N squared.
right? Okay? Is everybody following? Yeah, Jesse.
Quick question: if you were comparing two different T events, one of them is the one you have displayed on the board,
Yep.
and another one was n squared plus 1 without the n constant in the middle.
N squared.
Could you say that the top one is greater?
No.
No. Okay, because I'm just wondering.
No, no.
Well, as soon as we get into the
No, no, no.
degree,
Yeah, so that's the whole idea of the big O, right?
right?
We're
It's-
getting rid of those little minor details because, in a sense, it doesn't matter. Because if we're talking about really large n squared, that n term's going to go away anyway.
Okay.
And the 1 is going to disappear almost immediately, right?
Right.
So it doesn't matter. We're looking for classification so that we can compare different categories or classes of algorithms as opposed to trying to figure out what's the difference between these two that are in the same class. Okay?
So is it
Because we're going to be comparing, because what we're going to be comparing are these. So what's the category going to be for that? N times log of n. It's going to be in big O of n log n. How does that compare to n squared? Let's look at it this way. Okay, so this is n times n, right? This is n times log n. If we divide out the n's, how does n compare to log n? This is going to grow faster. Okay, right? That's the kind of thing that we're looking at, Jesse.
Okay.
We want to be able to compare classes of functions as opposed to comparing the functions within the same classification. All right. Because within like you said, within a couple of, a little bit of, constant
Wiggle.
time factors, they're basically the same thing.
Sure.
Do we need to go review our logs and all that kind
No,
of stuff?
no, you're fine. You're fine. No, you're fine.
I haven't touched that crap in years.
You just have to know the difference, you just have to be able to compare n and log n. And
What's the derivative?